Welcome to this video on fracture stability in the pore pressure workspace of WellCAD. An important functionality of the geomechanics workspace is the possibility to create output with respect to fracture stability. In this example, we see the image of an OBI optical televiewer and associated fractures that have been picked based on the OBI data. We also have different types of geomechanical input. We have pore pressure, PPG in black, the shear fracture gradient, SFG in green, and the maximum and the minimum horizontal stress, SH max in maroon, and SH min in yellow. These are the inputs which will be used in this fracture stability exercise. To access the fracture stability functionality, we start the geomechanics workspace by clicking on the icon. There is no need to select anything, just press OK. For this, we need some logs for the geomechanics workspace, and the logs that we would need are PIX, the OBI, the pore pressure, the maximum horizontal stress, and the minimum horizontal stress. Let's add the shear fracture gradient as well and the overburden stress. We drag them over to the geomechanics workspace and organize the data a little bit. And then we zoom into the interval of investigation. Once we're okay with this display, we click on the More Coulomb diagram icon and on the stress bar icon next to it. Now we proceed to the configuration of the More Coulomb diagram. We do this in the Properties bar, where we add the various components. We need to add the vertical stress or overburden stress, as well as the maximum horizontal stress, the SH max. At this point, we can see that the More Coulomb circle has been constructed, but only partially. We also need the minimum horizontal stress, SH min. We need the pore pressure, PPG, the friction angle and cohesion, which we can add later manually. In the Properties bar, we also have the More Coulomb display options that we will show you in a minute. So to construct the More Coulomb circle, we will need to select the fracture log, and in this case, the apparent PIX with nodes. So we select it, and now we have the different PIX in the More Coulomb circle. So there are more things that we can see in this display. For example, we can go for the normalized slip tendency, dilation tendency, or just fracture susceptibility. In terms of output units, right now we have them all in megapascals, but we can also change it to any of the units in the list. For convenience, we use megapascals. To view the data, go to the display section and see the plot that covers 5 meters of the recordings. We can see we have trend changes in the data. For example, around 3 meters, we can see the vertical stress gets bigger than the SH min. And as there are different intervals, so instead of having a More Coulomb circle that covers the whole visibility range, one can work on section by section. If we want to see how the More Coulomb circles vary over depth, we can select single point display, and we can move the mouse up and down after we select follow cursor. And when we move the cursor up and down, you can see the Mohr-Coulomb circle adapting to the different geomechanical conditions as defined by the curves on the left. We select again Visible Range Display and we zoom into the upper section for the first 3 meters. We can do that by pressing the Shift button on the key and rotate the wheel of the mouse. We can see the features much clearer now. So again, we select Visualization of a single point and follow cursor. And we move the cursor up and down as we can see the Mohr-Coulomb circles moving and adapting to the depth. We can see here around 3.1 meters where the vertical stress becomes bigger than the SH-min. There is a large discrepancy in the behavior above and below the 3.1 meters. When we visualize features in the visual range, we display all the different features in this section. We can also bring all features to display, and then we have more data points that can be displayed. But obviously this includes some features that are not within the depth range of the display view. They are in the lower section. So let's get back to features in visible range. We can modify the type of fill mode in the Mohr-Coulomb circle display. But before we do that, let's check out the wide view. We use it to display the envelope of different friction angles and cohesion values. For the cohesion, let's put 1. Now we see the envelope. This red line defines the envelope. And let's put a friction angle of 1 well. For example, let's put 0.5 for cohesion and try various values for the friction angle, and then use these values. We switch off the wide view. The envelope will now separate these features which are critically stressed as represented by the data points above the envelope. For these features, we can expect some slip tendencies, and for the ones below are the ones that are stable. So we can use 2 and 0.5 values for friction angle and cohesion respectively. We can see that most of the fractures are below the envelope, so they should be all non-critically stressed. We can now change the visualization of fill mode and select solid. We can see now in red those intervals that are critically stressed, and the intervals below in green are not critically stressed. We then modify the cohesion to 0.4, and we can now see that we have 4 features that are critically stressed. We can simply hover the cursor over them and get more details about them. They are also highlighted in the structure log. Now we can see that this is the fracture that is critically stressed, and this one probably needs further attention. We can also show the legend, but for the solid fill mode there is no legend. So we select the spectrum fill mode, and now we can see the legend. We can also select the palette, and we can access now to all the different palettes available in WELCAT. But let's go back to spectrum fill mode. We can also see here at the stress section in the properties where we can have output unit types, and they can be pressure or pressure gradient. And for the output units, we have all these various units. In the stress bar, we can visualize the different stress regimes. So in this example, in the upper part, we have the reverse fault stress regime in blue, and in the lower section, we have the strike-slip fault regime. This is something that can be very useful to visualize data. In addition, we can bring the image log into the navigation bar. You can just scroll up and down in the navigation bar to visualize the different parts of the data. So here in the lower part, we have this strike-slip regime. You can see the Mohr Coulomb circle is different. That is because of the associated geochemical data. We can also customize the visualization and the usability of the stress bar by clicking on these three buttons. Thank you for watching this video on the displaying of fracture stability in geomechanics workspace of WELCAT.